Okay, awesome. So I'll start quickly with an introduction of myself. I'm Steve Mustafa. I'm currently working with Salus. So Salus is a leader in workplace safety. I'm also an instructor at Dalhousie. I teach the tech innovation course. Before that, I used to work with SOTI. SOTI is the industry leader in business mobility. I used to be on the cloud team. We used to manage more than 5,000 servers living in Azure and AWS clouds. I graduated as a master's student from DAL in 2019 in computer science. My original bachelor degree was in computer and communications engineering back in 2014. Some notable projects are with the UNICEF. UNICEF helps cater for refugee issues. Before that, I was lead backend engineer with Carpolo, and Carpolo was Lebanon's #1 carpooling platform. Before that, I was also lead software engineer at Ideation Invest. We used to develop a lot of IoT projects, mobile, websites, and desktop apps. Before that, I founded Coolest Tech. One of the notable projects was implementing a home automation system controlled via brainwaves. Other than that, you can check my profile at steve.coolesttech.com. Just some of the projects I've worked on. So enough about me, and let's jump right into the PowerPoint presentation. To start with, please feel free to interrupt me whenever you'd like. Of course, feel free to unmute yourself whenever you want. I'll try to keep this as short as possible. In every slide, you will find lots of references, which are really highly recommended reads. So let's jump right in. This talk is going to be about introduction to NoSQL database systems. So databases, data warehouses, and data lakes. Anyone would like to tell us the difference between them? Anyone has any experience dealing with these systems? Nope. Okay, so to start with, databases are the smallest systems among all of these. We need databases everywhere. We need information to be stored somewhere. And so let's say, for example, we have a CRM system, ERP, billing, supply chain, any kind of system would require a database. Now, the thing is, with multiple databases, sometimes you need to do some visualization or business intelligence, or, for example, machine learning. So you would need multiple databases as if they are one, or to merge data from different sources in order to make sense of this data. And that's what a data warehouse is. It's basically the collection of data from multiple databases for the purpose of reporting, visualization, business intelligence, machine learning, and so on. Now, generally speaking, the database is structured. We know how information is going to be stored, and this translates into the modeling. Like, for example, with relational databases, we have predefined columns. In NoSQL, we still know which columns we are going to store in, even if it's in the form of a document. Like, we know the document has these fields and so on. Whereas in a data lake is basically just throwing raw information, either because we don't have the time to process them right now, or simply because we don't know how to process them. What this means is data lakes are raw and unstructured. We do not know how to specifically store them, what are the columns, how to make sense of the data. We do not know that. So we just throw them, save them as is, and then make sense of them. So processing schema on write. Whenever we're writing new information, we already know the schema. In data warehouse, it's the same thing. In data lake, it's schema on read. When we read this information, we try to make sense of it. Now, the cost could be free to cheap in databases. Data warehouses are a little bit more expensive. They could be developed in-house as well, which is usually not the case. Data lakes are cheap because they're basically just blob storage or some managed storage, such as with AWS and Azure, for example. Now, for agility, it varies a lot between databases, and we're going to see this in the next slides. It's minimal in data warehouses because these warehouses use a structure called ETL, extract, transform, and load. So we extract the information, we transform it, we apply some kind of filters, we apply some kind of data transformation or conversion, and then we save it in our new data warehouse. So as for security, I do not really agree with this chart. This chart is from one of these sources. I do think that database security is mature. It really depends on the database itself. We have RDBMS. RDBMS stands for Relational Database Management Systems, such as MySQL and Microsoft SQL. And I think they're pretty mature. Now for data lake, it's also been quite some time and they are becoming more and more mature. So I wouldn't say that these immature here are actually correct. Users, anyone uses databases. Everywhere we have databases. For data warehouses, usually it's about business users, IT, even data scientists, and data lakes are mainly for data scientists. And this is obviously because IT and business users would create the visualization, reporting, and business intelligence, and data scientists would try to run or model the raw information in order to try to make sense of it. Then we have use cases, so reporting, analysis, and automation for databases. And of course, the most basic use case is simply storing the information for retrieval, which is part of transactional processing, and we'll talk about that later on. And for data warehouse, we have machine learning, visualization, and so on. For data lake, we have data science and research, generally speaking. Now, I highly recommend reading all of the references which are included here. I'll actually send this PowerPoint presentation to Clara, and she would be able to send it to forward it to you guys. SQL, NoSQL, and NewSQL. So it really helps if we know a little bit about the history of databases. Anyone knows why or how we started with SQL? Why did we invent SQL? Come on, guys, let's keep this interactive. Okay, maybe I'm just too boring for you to participate. Well, of course, in the beginning, we started with very basic file systems. Whatever data you have, throw it into the file. And then overwriting the file was a big issue. Dealing with multiple input sources was a big issue. So for example, if you have two different users and you need to simultaneously accept some kind of request and then update the file, you need to queue these requests, do them one by one, make sure the new information does not overwrite older one by mistake. It was a total mess. Then we started thinking of ways on how to make this accessibility to this data efficient, whether it's writing or reading. And that's how database started. And SQL was mainly trying to reduce redundancy. So if we have some information somewhere, we do not want to replicate or duplicate this information somewhere else. And this is because at that time, storage was so expensive. Storage was actually more expensive than processing power. And that's why we see in SQL, we have what we call normalization. And this is what the meme is all about. Normalization is simply, for example, when you have an item and you want to say that this user, let's call them user one bought item one. And then you want to say that user two also bought item two. Now, as you know, in SQL, you would need to normalize, which means the item would go into its own record in the items table. And then you have the user, which is in the users table. And then because each user could buy multiple items, you need another table which says these users have bought these items, which is many-to-many relation, which translates into a new table. This normalization idea is because we do not want to store the same item multiple times. We want to reduce redundancy in order to reduce costs. Now, recently, the cost of storage has been decreasing like considerably, actually incredibly. And so lately, processing has become much more expensive than storage cost. That's how NoSQL started gaining popularity. Because with NoSQL, you have redundant information. Like if you have multiple people buying the same item, you could duplicate this item information in each record, in each document of the user. Like the user bought this item as a subdocument, and this subdocument is replicated many times per user. Why? Because it's cheaper than having an additional table and then making the necessary joins. Now, of course, this is a very broad topic. There are many details. I'll keep it up to you to ask. So whenever you have any questions or you'd like to go into more details about any idea, please let me know. I'll try to keep this as quick and simple as possible, but please let me know if you have any questions. By the way, do we have anyone here who has not worked with a database before?
I haven't worked with anything before. I joined very unprepared.
Oh, that's perfectly fine. So to give you just a little perspective, a database is where we save all the data. Like, for example, let's say you are a bank and you want to say, we have these customers. So these customers go into what we call a table. Now, a table has some fields. These fields are, you can think of them like attributes. What does this customer have? This customer, for example, has an address, has a phone number, has a first name, last name, and so on. And then you need to keep track of the transactions that this customer has. Like this customer has bought using their credit card some item, or they have a balance of this much, or they have deposited this much money. So the database is where all of this data lives. Now, because you have a lot of requests coming in at the same time, your database should be able to cater for all of these requests efficiently. You do not want, for example, let's say we have, for example, just hypothetically, we have 1 million transactions going on with MasterCard, like 1 million people around the world at the same time or within 1 second making a payment. You do not want to process them so slowly that one of them would have to wait, let's say, an hour, as in the case of Bitcoin. Like when you make a Bitcoin transaction, it could take 10 minutes, 15 minutes, half an hour. So this is definitely not usable with our advanced, let's say, credit card scenario where you just want to tap, a few seconds, it's done. And this is why we have many kinds of different databases. So SQL is structured querying language. NoSQL is not only structured, so we have more options. And we have NewSQL, which is literally trying to bridge the gap between SQL and NoSQL. Does this make a little bit more sense?
Yeah, for sure. I think I'm following along so far. Well.
Awesome. Yeah, feel free to ask any questions. We've got a lot of time. I made sure the content I'm presenting is actually less than an hour, so please feel free to ask whatever you'd like. So for SQL databases, we've got MySQL, Postgres, VaultDB, Yugabyte, and so on. Now, all of these, the ones I mentioned, are SQL. However, they differ in the way they scale. And this is actually not so true anymore. I'll tell you why at the end of the slide. So with SQL, you replicate the data. So let's say, for example, you want to cater for more customers. You want to cater for 1 million customers at the same time. What do? You have one master node. So you have multiple servers hosting the database. One of them is the master. So whenever you write to the master, and the master updates all the other nodes. And when you read, you could read from any of them, or the rest could be just for backup purposes. But usually when you're scaling, you want to read from the other ones. So what happens here is you replicate the data in order to scale. On the other hand, sharding is where you split the data into multiple servers. What this means is, let's say you have a table of users and you have around, let's say, for example, 1 billion users. What happens is, let's say you have, hypothetically, just to make the numbers easier, let's say you have 2 instances of the database. One instance would take 500 million and the other instance would take the other 500 million. So now when you say search for this information, each of these 2 instances is going to apply these search filters on its own data set. And then after they're done, they're going to combine the results and give it to you as if it was one instance processing the whole thing. This is how parallelism works with sharding. And then we have multiple data centers. Now, the thing with multiple data centers is that it's quite common now, whether it's with replication or with sharding. However, the original concept is that the instances do not even have to be in the same data center. Like it's even more flexibility. Now, as I said earlier, this is not completely accurate because these databases have been evolving very quickly, extremely quickly. So in 2018 or 2019, I think MongoDB has become ACID compliant. We are going to see what's the difference between ACID and base in a few slides, but keep in mind that these databases have improved quite quickly in a way that this isn't very accurate anymore. The differences have become so blurry. So then we have the column family. Column family is, let's take an example in Cassandra. I think it should be Cassandra data model. So let's start a browser instance in here. Oops, Control T. Okay, so this is an example of Cassandra. One row could have 3 columns where the other could have only 2 columns. Unlike SQL, where the columns apply to all the records, even if you have to set it to null. So just keep this in mind for a few seconds while we talk about MongoDB. So I'm going to show you an actual MongoDB instance. Now, MongoDB is a NoSQL document database. As you can see here, it's MongoDB multi-data center document data store. And what document data store means is this. Some of you might have attended the previous talk where we created the demo app in Node.js. Anyway, this is the result of it. Oh, well, we don't have any expenses here. Okay, I'm sorry for this. It's fine. I can just show you something from the internet. So in MongoDB, we have multiple documents, and each document could be completely differently structured from the other. So this is one document, for example. We are getting the employee. We are saying find the employee. So the employee has an ID, has a name, has an age, branch, department, and salary. Now, the other employee does not need to have the same fields. So let's say this one has name, age, branch. Maybe the second one is going to have first name, birth date instead of age, and so on. Like they do not really need to look similar or to have anything in common, basically. And one item could have nested items inside. Like you could say, for example, work, and inside the work, you have a nested document inside it, which says work ID, work name, the address of the work, and so on. Is it clear a little bit?
So far, so good for me.
Okay, thanks. Yeah, and this is another example of relational databases such as MySQL and MS SQL, where you have a table. So all users need to have these 3 fields. Each user needs an ID, needs a media ID, needs a name, and so on. And if a user does not have one of these, then you set it to null. And in relational databases, because the schema is predefined, you can enforce some relationships. Like, for example, if a user bought an item, make sure that the item ID, which I'm inserting, exists in the items table. Or, for example, make sure that what I'm inserting in the name is a varchar, which is kind of like a string, basically. So you can enforce the type of the information, you can enforce the integrity of this information as well, which is not usually the case in NoSQL databases, where these rules should be enforced by the software itself, not managed at the database level. So let's get back in here. So we talked about SQL, column, document. So now you can see that Cassandra and column family and document family is actually very similar. The main difference is what you can find in here. How does column-oriented NoSQL differ from document-oriented? Generally speaking, column family only allows a specific number of nested documents, which provides you better performance. But if you need multiple levels of nested documents, then you go with document. And then finally, we have the key value store. Key value is basically like an associative array where you say, for example, let's write it here quickly, my array of field 1 equals, for example, value 1. I'm going to move this just so that you can see it. So I have an array, and I say it's an associative array. So I give it the field 1. It's like a dictionary, if you're familiar with Python, for example. So I say my array of this field, and it gives me the value. This is basically the key, and this is the value. So key value stores are usually used for caching. I just give it the URL, it provides me with the data, or could be used as a very big in-memory array where I need to run some extensive search filters and so on. Databases, how to choose which database is good for you. Now we have what's called the CAP theorem. To put it simply, it's like cheap, fast, and good, but you can only pick two. Technically speaking, you can only have two of these three. You can have consistency, partition tolerance, and availability, but only two of them. Usually we have partition tolerance. So it's either CP or AP. Now, maybe 10 years ago, RDBMS such as Microsoft SQL, MySQL, and Postgres used to be CA, which means they are consistent and they are available. Now, what does consistency mean and what does availability mean? Let's see the CAP theorem. So consistency means that all clients see the same data at the same time, which means that if I have multiple instances of my database and I just updated one of them, it's unacceptable for some client who is accessing a different instance to see inconsistent information. If I have two clients and each of them is accessing a different instance and I just updated one of these two instances, then both of them must see the same information. I cannot show one of them the new data and the other the older data. This is what consistency means. At all times, all instances have exactly the same information. Or at least when I'm reading the information, it's the same. Now, as for availability, it means that any client making a request gets a response, even if one or more nodes are down. So if I have multiple instances and one of them is down for some reason, I can still serve this information using a different node. And then we have partition tolerance, which means if one partition is lost, or the connection is temporarily delayed between two nodes, my app should still work properly. Partition tolerance means that the cluster must continue to work despite any number of communication breakdowns between nodes in the system. Okay, so let's go back to our PowerPoint. You can read more about the CAP theorem, why we cannot have all three together from these links. They are really good. I just don't want to put a lot of time because it's a little bit complex, especially when you're new to it. So I think these are very good resources to find the relevant answers. Just keep in mind that with partition tolerance, we either have consistency or availability. So either that all the nodes return exactly the same information at the same time, or that they're all available. The app is always available, even if some nodes are down. Now, also keep in mind that there are always workarounds. Like you could actually achieve these three together by merging multiple systems, like one system which is CP with one system which is AP with one system which is CA, and they talk together, and it gets complicated, and you don't really achieve all three together exactly, but you're as close as possible to achieving all three together. And one more thing before I move on is each of these databases like Bigtable, MongoDB, RDBMS databases, Cassandra, CouchDB, and so on, all of these are improving very quickly, that some of them are actually configurable. Like RDBMS now, for example, you can choose, do you want it to be CA or CP? Some of them even CA, CP, or AP. And of course, when you choose one of them, it doesn't mean that the third one is totally non-existent. It just means you're prioritizing two of them over the third. Okay, what if I told you we're going to need a bigger database? Databases, how to choose. Another thing when choosing, other than the CAP theorem, is OLAP, HTAP, and OLTP. Now, the thing is, we have database which are best used for online analytical processing, which means you're analyzing some information, you're getting some relations, making sense of data, and so on. And then you have online transaction processing, which is very similar to what banks have. For example, I care a lot about transactions. I want to make sure when I move $5 from a customer's balance to another customer's balance, I need to make sure that this is optimized, not the analysis part. And then we have the HTAP, which is a hybrid in between the two. For more information, why we can't achieve all of them at the same time, why it's not so ideal in the real world, I recommend these resources. And then last but not least, we have base and acid. Base means basically available, eventually consistent, and it has a soft state. I'll tell you what this means in a few seconds. Let's start with the acid actually. So it's atomic, it's consistent, it's isolated, and it's durable. Now, a very interesting example on atomicity. What does atomic means? If I want to transfer $5 from customer A to customer B, how do I do this? Can someone please unmute yourself and just let me know what are the procedures you would need in order to do this? We need to move $5 from customer A to customer B. Let's say it's a Interac e-transfer. What should we do? How do we?
You need to check if the customer sending the money has that amount of money in their account.
Yes. So let's skip the validation part. You're right. We need to validate. Does customer A even have $5 in their account or not? Let's say we are sure that they have the $5 and we are sure that customer B exists and all the validation is good. Now, how do we transfer the $5?
You subtract 5 from customer A and then add it to customer B.
Awesome. So customer A balance minus $5, and then customer B balance plus $5, right?
Yeah.
Now the problem is, what if I subtract $5 from customer A, and then for some reason my database shuts down? There's fire in the data center and the hardware fails before I add this $5 to customer B. Now, this is what we call atomicity. It means I'm going to do these two. It's either that both are going to fail or both are going to succeed. I cannot end up with customer A having a balance -5, and at the same time, I have the same customer B balance. It's either I moved the $5 or the $5 stayed where it currently is. Now, how this is done, again, I recommend these sources. Like I would love to go through it, but the thing is, I really want to reach the graph database part, which is way more interesting. If you're interested, we could actually have another talk detailing how these things work. But this is what I really wanted you to know. Atomic means the data is consistent even if you have multiple transactions and one of them failed. Okay, when you have this atomicity and this consistency and this isolation, you're adding more overhead, which makes things a little bit slower. With large systems, things could get significantly slower. And this is where Bayes came into existence, because let's take an example other than banks. Let's say you analyze the sentiment of your customers, like you have some kind of survey, and it doesn't really matter whether the data is delayed or not. It doesn't really matter that you get the latest up to the millisecond information. If you get information which is 10 minutes old, it's really not a big deal. So for this use case, you really need the quickest processing you can do, even if it's not like up to the millisecond consistent or up to date. It is going to become eventually consistent. It's basically available. And soft state means that it doesn't really need to be structured. Like, let's say you're running some machine learning on Twitter feeds or tweets in general. Not all tweets are going to have the same structure. So let's say you are trying to detect some features in these tweets, then you could have each record have a different structure in the same table or in the same document store, for example. This is an example on atomicity. Backups and replication. Your database is corrupt, but your backup is fine. I heard you lost some data. Too bad. If you liked it, you should have backed it up. So this goes back to always backing up your database, having replication sets. Yeah, we already talked a little bit about this. And now to my favorite part, 6 degrees of separation. Any questions until now?
I'm over my head a little bit in terms of databases here, so it's interesting. Yeah, I'm learning here.
Any questions or something you'd like me to explain more in more details?
Not really, but I'm going to take a look at the links that you provided here because it'd be helpful in terms of getting some more context for it. I've really only worked with like MySQL like in a limited way. What do you think is like the, I guess like the easiest, not easiest, but what's like a good starting off point to like start approaching something like NoSQL? Like MongoDB is a name that I hear thrown out a lot.
Yeah, totally. For every use case, you could have a best case database, let's say. In some solutions, we even have what we call a polyglot. Now, I would say never go with a polyglot unless you really know what you're doing or unless it really gives you a huge edge. A polyglot means you are using multiple types of databases in the same solution. And not to be confused with polyglots where data is not synced in real time. Like, for example, I remember once working with a startup which does matching between people, like something similar to Tinder. So what this startup did is they started with an RDBMS, something like, I think, Postgres maybe. And so the problem was when they wanted to recommend something, it was much better to use a graph database. And we are going to see graph databases in action. So they wanted a graph database, but they did not have the time to rebuild the whole structure of their app in order to cater for graph. So what they did is they would take a full snapshot of their RDBMS, which is Postgres, and they would migrate it into graph, run the algorithms and machine learning they need to run, and then import the recommendations back into the RDBMS. And so the API never talked to the graph database. The API only talked to Postgres, and they had some other kinds of scripts or pipeline, which every day got the new information, processed it, and filled back the recommendation. In my opinion, this is a very smart approach if you don't have the means to restart or rebuild your solution, especially at the early stages. I think it's a very smart approach. However, another type of polyglots is where you could be using both or multiple kinds of databases at the same time, and you need them to be up to date. You need to make sure they are in sync. You need to build your own rules in order to make them work together. And this is very, very difficult. Any questions before we move to 6 degrees of separation? Have you heard of it, guys?
The 6 degrees of Kevin Bacon is the one people sometimes talk about.
So 6 degrees of separation is a theory which was to some extent validated by Facebook a few years ago. What this theory proposes is that you can be connected to anyone in the world with only 4 people in between you two. So let's say this is you. You know someone who can introduce you to someone, who introduces you to someone, who introduces you to another one, who introduces you to whoever you want to get introduced to, a random person in the world. So at most, there's only 4 nodes between you two. This is, like, to me, this is amazing. This was validated by Facebook recently, 2016 or 2017. They used to have a web page where you can go log into your Facebook and it would tell you your own score based on the Facebook network. So it would tell you the average node between you and any other random person on Facebook. And very interestingly, like my average was around 3 point something. Most people fell between 2 and 4, which is amazing. Like, think about any person you would like to meet. For example, Elon Musk, I don't know, Justin Trudeau. Maybe Justin is like within Canada, so it's less hops, but think maybe, I don't know, someone in a completely different country whom you've never met before. And the way it works is something similar to this. So let's say this lady over here wants to connect with this guy over here. So this needs to connect with this guy, introduces her to this lady, this guy, lady. Honestly, I forgot which one we started with, but this is the concept. Now, how it actually works is something like this. So is it clear what the 6 degrees of separation is?
Yeah.
Okay, so now I'm going to show you an example between SQL and graph databases. Graph databases are extremely efficient when it comes to nodes. Or if you think about the Dijkstra algorithm, which calculates the shortest path within a graph, this is where graphs work best. Like you have someone who's friends with 50 people, and each of these people has 50 friends, and you need to see between this guy and this guy, how many hops are there, which path is the shortest, and so on. And this is usually used in social networks such as Facebook, LinkedIn. I'm not sure about Twitter, but I think they are using it as well. Now, this is an actual example of how graph and SQL fare when it comes to this kind of situations or cases. So determine if one person is connected to another in 4 or fewer hops. So think something like LinkedIn recommendation system. Yeah, like it wants to show you someone that you could connect with. So they took 1,000 users, and each one of these users has 50 different friends. So 1,000 users, each user has 50 friends. It took 2 milliseconds to figure out all the people who are connected within 4 or fewer hops in graph database. Now in SQL, it took 2 full seconds, which is 1,000 times faster in terms of graph. Now they were unsatisfied with the result. They said, okay, what if it's among 1 million users? So 1 million users, each user has 50 friends, and we need to figure out the people or the people who are connected to other people within 4 or fewer hops. It still took 2 milliseconds in graph. It took several days in SQL. It did not finish. They just got bored after several days and they shut it down. So this is just to give you an idea of how efficient graph databases are when it comes to relationships as compared with SQL. Is it clear? Any questions?
Yeah, I'm just kind of curious, like, how do you structure a graph database that makes it different than like something that's column based? Like, so for each of the relationships, you're going to have like, it's like a doubly connected graph, right? Like you have each node and the connection between them. You have, this person is friends with this person. And then also for that person, you would have the relationship back onto itself. Now, like in a SQL database, that's all going to be saved in columns, right? So like, for each user, they have their own database, or you have like a complete database of like all the relationships between the users. Whereas I guess in the graph, they're each going to have their own like sort of like table, right?
Okay, yeah. So actually it's in the next slide. Just to correct some things or to make things clearer, we have tables in SQL. So users have their own table. They don't really need their own database, right?
Yeah, sure. That's what I meant. Like there's a table for each individual user instead of just having a total table that has like all of the relationships of the users like identified by an ID or something like that.
Yes. So in graph, it's a node. So each user is a node, and each node has its own properties. It does not need the properties to be common among all the user nodes. Like one user could have a first name, last name. Another user could just have full name. One of them could have age property. The other would have date of birth. They do not need to be the same. You could enforce it through your code, but not on the database level. You know what I mean? So it's similar to document store.
Yeah, for sure. It's kind of like
yeah.
JSON. It's reminding me of JSON in some ways, but like also it means you don't have null values that you have to keep like space for memory for, I guess.
Well, luckily, you do not have to care about memory. These databases are well optimized to cater for this without you having to worry about memory. So this being said, I just need to remind you that even RDBMS databases now do have JSON fields. So if you wanted to actually store a document in RDBMS, since a few years ago, it has become possible. And this is why I told you in the beginning, the lines have blurred a lot. A lot of RDBMS systems could be considered a NewSQL now, and a lot of NoSQL could be considered NewSQL as well. You know what I mean? That's a lot of wells in the same sentence.
Yeah, I think vaguely, but like the root of the term like SQL, like structured query language, like you can access the data in any of these database management systems just using like conventional like SQL that
The thing is,
In terms
even
of scripting, I guess, or in terms of querying.
you know, with Postgres, for example, you use the you use this notation. So let's say you have a column, so you have a user table, and in the user table you have a column which is let's say user address, for example, address, and this address is of type JSON. So now the document you have is actually queryable. So let's say you have postal code, and then you have province. In the query, you could say select, for example, star from users where address like this province equals ON, for example. You could do this, and this field is JSON. So, and this is what I'm trying to say. Databases have evolved amazingly that you can actually have an SQL database act as if it's a document store. Now, of course, it's not meant to be a document store. So if you have multiple nested levels, it won't be as efficient, but it's doable. You know what I mean?
Yeah, I think I follow. Like, so like storing a JSON object as like a element in your table is something that's sort of new and novel in databases recently.
Yeah. In RDBMS specifically, because with NoSQL, the default is unstructured JSON anyway. Yeah, so just keep this in mind. Databases have blurred the line quite a lot. Okay, so this is how graph databases work. We are actually going to test one together. So just keep in mind, there are only two types of structures, really. We have a node and we have a relationship. This is it. If you have a user, the user is a node. You have another user, that's another node. You have an item, that's another node. And then you have relationships between them. Like, for example, we have here name is Marco, the age is 29. They know another person. They create a language. Maybe it's a job or something. And this language was actually created by two people. As you can see, they collaborated on it and so on. Now, full managed databases and serverless. I don't think we have the time to go into serverless architectures. We usually have a separate talk about that. Just wanted to mention that we do have fully managed databases, which means that you don't really need to worry about how the database is storing things or how it's optimized or how it scales internally. All you care about is, I want a document store. I'm going to use it right away, such as with, I forgot honestly what the names were, but if you go to AWS managed DB, yeah, there's RDS in Amazon, which is relational database, but it's managed. And there's another one for NoSQL, but honestly, I forgot the names right now. Anyway, you can look that up if you're interested. Okay. And then we have polyglots. We already talked about polyglots earlier, where you could have a graph store for some information, and then an RDBMS for some other information, and then a document store, let's say for logging, and key value store for caching, and so on, as opposed to only having one database catering for everything. If it's not in the database, did it really happen? I'm just going to take 5 more minutes. Let's go into Neo4j. I'm going to remove this out of the way, and let's go to Neo4j. Oops. Neo4j Sandbox. I highly recommend this. It's amazing. This is actually a newer service. We used to have to set up a graph database locally in order to test it. And now this sandbox is just amazing. If you go to sandbox.neo4j.com, select the movies. Well, you'll have to register first. It will ask you to register. It's free. Once you register, you choose the create a new project, select movies, create. So now it's going to create a new project for me, and it's going to be sandboxed. It will only live for 3 days. It's going to be deleted after that because it's free. Of course, you can pay and retain the information, but now we're only interested in just checking it together. So we're waiting for it to create the sandbox for us. Then it should automatically load. So just general feedback. Do you think the pace was good? Was it too boring? Was it a little bit too fast?
It was pretty good. I think it funneled well, or I guess the path was pretty good. But there were moments where I felt like we jumped topics and then we went back. I couldn't recall exactly. I'd have to look back at the slides. But generally, I liked it. I think it went from general or like I had no idea what databases were, but then I could keep up pace, so that's a good sign. Like the beginning information helped me understand when you were talking about base and acid and stuff like that. I guess stuff like the server, something that you jumped over, I didn't know how that would fit into everything. So like,
Yeah.
does that make sense?
Yeah, totally. Serverless is a big topic. I usually give a separate talk about it. Yeah, I just wanted to make sure that you guys see how graph databases work, because I got hooked on it once I tried this example. So just to give you an idea, because I know Liam and Pritam have worked with SQL, I'm gonna select all the movies. So this is what match is. Actually, I'm just gonna select all the nodes. So match is equivalent to select. What's the problem? Cannot conclude with match. Oh yeah, I forgot the return statement. My bad. So I'll just put this, return and remove the limit. And remove the conditions and keep M. Okay, sorry, it needs to be in parentheses. And so these are all the nodes we have in the graph. And you can see how visual it is. I should be able to zoom in somehow. Honestly, it's been quite some time. Oh, here it is. Yeah, so this is my graph. It automatically created it based on a movie database. So if we just zoom in a little bit, we can see.
Yeah, this is super cool. This just like generated it for you.
Exactly, yeah.
Okay,
So
that's it. I've done like sort of like making interconnected graphs with R like in our studio before, and it's like a hassle. Like I mean, it's not a huge hassle, but you don't just get like, you know, your queries like returned to you in a visual way like this. This is really neat.
Yeah, so this querying language is called Cypher. It's amazing. Of course, we're gonna see it in action. So you can see here, if I click in this one, for example, I can see when it's released, when the tagline, the title, who acted in it, who was the director. Can you see all of this? Like acted in, directed by, and then you can do all sorts of amazing queries. So let's actually do this. Let's say we want a movie which was released after 2000, and I want only 5 of them. So these are the 5 selected movies which were released after the year 2000. Now let's continue with the predefined path. So now match a person who directed a movie where the movie was released after 2010. So we have 3 directors who contributed to Cloud Atlas. Now let's say next, match person, return limit, match and return limit. Okay. Match a movie. Okay, so let's say I only want the title and the release date of a movie. So I can, this is like a select, instead of star, you are actually selecting the fields you want to show. Okay, next. So this is how you insert. You say create. Now notice that these parentheses are the nodes. Remember that we have nodes like this and then relationship and then another node. So this parentheses here, these two, mean that this is the node. Now this node, I'm giving it a variable name called P, which is in SQL is equivalent to as. So select the type of the node is a person, where the name of this person is John Doe, and as P, and then the return P. Do you see how it's working? So now when I return this, it returned John Doe. Now this is where things start to get interesting. Match a person where name is Tom Hanks, where p.name equals Tom Hanks. It's the same thing. Next. And I don't want to go into on. Do they not have? Okay, this is the one I'm looking for, I think. So match a person with a movie where the person name is Tom Hanks and the movie title is Cloud Atlas. Now I want this person, which is Tom Hanks, to have a new relationship with this movie, and this relationship is called watch, and return the relationship. Now, instead of returning the relationship, I'm going to return P dash anything dash M. So now I can see that Tom Hanks acted in Cloud Atlas, and because I just added a new relationship, he also watched it. And you could see from here, it's, see this, watched, this arrow here, it shows the direction of the relation. So P watched in this direction M. If I created it this way, in here I added the other direction, it would have become the opposite. The movie watched Tom Hanks. Now this is not the, okay, now this is very interesting. I'll just remove these so as to clear a little bit of RAM. Match a person who acted in any movie. Now for our case, I want the actors of the movie, which is Cloud, the name, I think, the title is Cloud Atlas. Okay, so this way I've got all the actors I have in my database in Cloud Atlas. You see, it's pretty simple. Match the nodes of type person, call them P, where they have a relationship, ongoing relationship, which means this way. Of course, if you have double relationships, you can do it, just remove the direction. Or if it's on the opposite side, you can just do this as well. So I want the relationship acted in, call it R, and the movie which has this title, call it M, and return the person, the relationship, and the movie. Is it clear what's going on? Isn't it amazing? Okay. Like, you know, guys, if you wanted to do this in SQL, this is at least 1 or 2 joins with proper indexing, with foreign keys.
Would be awful.
Yeah, and especially when you have multiple hops. So I know I'm over time. I'll just show you multiple hops. Now imagine this in SQL. Match Tom, let's call him Tom, who is a person, and the name is Tom Hanks, acted in a movie, and we want the co-actors from any other movie. So I didn't specify which movie, and I'm getting the acted in person, and I want this person name. So if I just run this, we won't know what happened. So I'm gonna modify it a little bit. I'm gonna say return Tom and return R1 and the movie M, and R2 and P. Now look at this. This is amazing magic. We have Tom Hanks here who acted in this movie, and we got all the co-actors of Tom Hanks in this movie. See, actually in all the movies of Tom Hanks. So all of these leaves are actually the co-actors in any movie with Tom Hanks. Now imagine this in SQL. And imagine this, I'll end up, this is the last one, I promise. This is, I'm just too excited, I'm sorry. Now this is the last one. So match person whose name is Kevin, and there are 1 to 3 hops with another node, and return P and the node. So look at this. This is Kevin. Any nodes within 1 to 3 nodes in between. So this is the first node, this is the second node, and this is the third node. So it got all the nodes in between. Okay, so I'm gonna end up here. I hope you enjoyed this as much as I did. Any feedback is most welcome. Please let me know if you have any questions, and thank you for being here with me today. I'm gonna share, yeah, go ahead, sorry.
Oh no, I was just curious, Steve, have you ever heard of dplyr? It's a library for R. I think it doesn't, I mean, it doesn't seem to show, I don't know a lot about Cypher there that you were demonstrating, but I want to look into it because some of the, like the piping syntax in dplyr, and yeah, it's just, it kind of reminds me of it in a vague sort of way. It's also really interesting, like way of like manipulating and sorting your data.
Totally. There are actually multiple querying languages for graph databases. Unfortunately, one of the most common is SQL. Like you actually write SQL to get information from graph, which I totally hate, honestly. But I understand where people are coming from. Like they're used to SQL. The Cypher has some learning curve. I totally understand. But if you have the time to learn Cypher, it's just amazing. And if the library you're talking about is very similar, then awesome. Okay, yeah.
Thank you, that was fun. Yeah.
Most welcome. So I'm going to send this PowerPoint presentation along with the recording to Clara, and she's going to contact you with these resources. Any questions or any feedback? Okay, thank you so much, guys. Enjoy the evening.
Thank you, you too.
Have a great one.
Have a good day.